Stokes equations. And they also try to make connections with the other uniqueness result about two-dimensional Euler equations. Let me just rewrite down the statement. So there exists an external body force, which is at least L1 time L2 space, and two distinct Leray solutions Stokes equations with body force F and initial condition, initial velocity simply 0. Okay. So the key elements of proof are self-similar dynamics or evolutions. Some form of instability, symmetry breaking, and all of those elements give me uniqueness. Let me start by talking about self-similar solutions, so self-similar evolutions. So we have seen that Navier-Stokes has a natural scaling. Given a certain parameter lambda, you can scale down the velocity, the pressure, and the external body force, and the equation is invariant under this scaling. And self-similar solutions are exactly those solutions invariant under the scaling. What I mean is the following. So peak U PF solutions to S. Now, if we scale U according to the scaling of the equation, and then do the same with P and F, we know that this is another solution to Navier-Stokes, but it can be a different solution, right? Being self-similar means that this is equal to U itself. And similarly, just write the pressure. When this happens, we say that the solution is self-similar. So in a certain sense, self-similar solutions are those solutions living at the critical scaling of the equation. Exactly at the critical scaling. And now, and of course this identity has to be true for every lambda positive, for every scaling parameter lambda. And now it's a super easy exercise to check that a self-similar solution can be actually expressed. So fix any x and t. If you pick lambda squared, if you pick lambda such that lambda squared t is equal to 1, here you get rid of the time dependence. And what you get is the following identity for self-similar solution. So uxt has to be equal to 1 over square root of t, capital U of x over square root of t. For a certain capital U, which is the self-similar profile of small u. And I mean, the same thing for P, but let me just write down what happens for F. You get 1 over T, 3 half, capital F of x over square root of T. And capital U and capital F, and also capital P, the one associated to the pressure, are called the self-similar profiles. interesting is that we can understand these solutions are as steady states of Navier-Stokes equation written in a special set of coordinates. Those are the so-called subsimilar coordinates. My new space variable is xc equal x over square root of t. And my new time variable is tau equal log t. And notice that now the time variable lives in minus infinity plus infinity. And notice that the origin in standard variables, t equal to 0, now corresponds to tau equal minus infinity. This is going to be a very important equation later. Then, if I have u, p, and f, two velocity fields and a scalar, I will write u of xt as 1 over t 1/2 capital U of c tau. That's just a way to, it's just a change of variables if you want. And I'll write pxt as 1 over t capital P of c tau. And finally, f of xt 1 over t squared capital F of c tau. And I use this notation, so anytime I have a velocity field, it's going to be in physical variables, in standard variables. I'll write it in small letters. And the associated subsimilar profile will be written in a capital letter. But so far, this is just a general variable. So here I'm not assuming anything on capital U, P, and F. So capital U is that vector field such that this identity holds. While here, I was assuming that there's no dependence on tau. So here I'm assuming something, that's just a change of variables. Now, assume that U, P, and F solve Navier-Stokes equations, we can break down an equation for capital U, P, and F. And this is exactly Navier-Stokes in similar coordinates. Let me denote it by an SS. And it reads as follows. We have d tau of capital U minus a new term, 1/2 1 plus c dot grad U. Then the usual diffusion, the usual nonlinear term, the pressure, and the wafers. That's it. And of course, we have the incompressibility condition as well. And now I'm solving in C in F3, and the time variable in minus infinity, say, if the time interval in physical variables were 0 t, now I have minus infinity log t. So in a certain sense, in this new set of variables, we are looking for ancient solutions to the equation. And now, at the level, let's just check the equation at purely analytical level. Essentially, an SS corresponds with Navier-Stokes. The only difference is the diffusion term. I like to think of the sum of these two as the new diffusion. In time, at the analytical level, if you don't change, if you put t here, for instance, when you look at the evolution, you don't get a closed equation in capital U. You get terms like 1 over t around. So the only scaling giving you an equation depending only on the similar profiles, capital U, capital P, and capital P is the logarithmic scaling. This is more like a technical answer than heuristic, but I hope it's enough. Okay. Okay. The equation is essentially, yep.
So where is eta? So is it just set 1?
Eta.
No, sorry.
Thank you very much. Let's fix from now on nu equal 1 for simplicity. No one to write nu many times. So we are dealing with Navier-Stokes. Forget about Collier for a while. Nu will be 1. Thank you. Yes. It's capital. Yeah, there's. I mean, yeah. Thank you. That's capital P. Okay. Yeah.
Did anything else happen from the left board to the right board? For example, the F has a different prefactor.
F has a different 3.5. Oh, yeah, that's a mistake indeed.
And then on the left board, the U and the F only depend on
yeah, here the point is, so that's a notion of self-similar solution. It's a particular solution.
Okay.
And I'll elaborate more on the connection between purely self-similar solutions and standard solutions, but written in a new coordinate. Okay? And thank you for spotting this. This was a mistake. Anything else? Great. So, Navier-Stokes in self-similar is essentially Navier-Stokes with a new diffusion, which is Laplacian plus a certain transport term. Let's give a name to this diffusion. I'm going to call it A of U. Okay? And it turns out that this is pretty good. It's better than the Laplacian in R3. Indeed, we can check the spectral gap property. So it turns out that the spectrum of A, the set of singular values, is contained in the half space of complex number with a real part strictly smaller than -1/4. This is going to be very useful in the sequel. That's much better than what happens for the Laplacian. Adding this term shifts the spectrum by a tiny bit, -1/4. And you can check this. The easiest way to figure this out is by essentially integrating by parts. So you have the following identity. If you integrate U against AU, you take the integral, integrate by parts, this is going to give you the integral of the differential of U squared plus 1/4, here is the magic 1/4, U squared. Now, imagine that you have an eigenvector U with eigenvalue lambda. Test this eigenvector here, and you realize that lambda has to be bigger, but the real part of lambda has to be smaller than -1/4. I mean, this is not the proof, it's just a formal check, but it can be proved. Okay. So we have the very same set of equations with a slightly better diffusion, but now we have to solve up to -infinity. Now let's go back to self-similar solutions. What are self-similar solutions in these new coordinates? Nothing but the steady states of the NSSS. So essentially, by definition, self-similar solutions are those solutions of Navier-Stokes such that they don't depend on the variable tau when written in self-similar coordinates. So, UPF self-similar solution then capital U, capital P, and capital F is a steady state for the self-similar evolution. Okay? So now we have these steady states, And the natural thing to do is to check whether they are stable or unstable, and try to understand what's the meaning of stability and instability in such similar coordinates in terms of uniqueness or no uniqueness of the resolutions. And it turns out that, and this is the whole point of this construction, that instability in self-similar variables leads to non-uniqueness. In standard variables. This is the whole point of the construction, and I'll try to elaborate more in this talk. Of course, before asking any question about stability and instability, we wonder whether subsimilar solution exists. This is going to be the very first question. So existence of subsimilar solutions. So we start, if we want to build a subsimilar solution, our data have to be subsimilar. So it's natural to pick an external body force, which is subsimilar, and an initial condition, which is subsimilar as well. But here is the first easy observation. If you have a subsimilar solution, the initial condition, which is u at time 0, is going to be -1 homogeneous. Because if you plug t equals 0, what you get is lambda u lambda x equal ux. So the initial condition has to be -1 homogeneous, and -1 homogeneous amounts to the following. 1 over modulus of x times a certain angular function defined on the sphere. Now, our goal is to disprove uniqueness in the class of the resolutions, so we would like to build self-similar solutions within the energy class. And notice that if alpha is different from 0, this object is more or less 1 over modulus of x. It is L2 locally, around the origin is L2, is almost L3, but this is no surprise because we know that L3 is the critical space, and the similar solution are exactly critical. But this is not globally L2 because it decays too slowly at infinity. So what I do is then assume that the initial condition is 0. We pick a good external body force and 0 initial condition, so why not? In the end, in our theorem, the initial condition is 0. So. There are results about building similar solutions with initial condition different from 0, and body force equals 0. I will simply go for 0 initial condition and the non-trivial body force. It's a choice, okay? So the initial condition will be 0, and there's no point in assuming a bad or non-regular similar profile. I want to make things very, very easy. I'll assume that F is smooth with compact support. A very beautiful similar profile. And now the question is, can we build, given such an F, and given the 0 initial velocity, can we build a solution, a subsimilar solution, which is also Lere, a subsimilar solution within the Lere class? And we know that in order to build global solutions, notice that subsimilar solutions are naturally global. Once you have them at time 1, you have them for every time. It's written, essentially the definition. So once you have capital U and capital F, you have them for every time. And we have seen essentially 2 methods to build global solutions. One is about small data in critical spaces. And under these assumptions, we have seen that we get also well-posedness and uniqueness. And we have seen a second method, which is essentially how we build the resolutions. And this is essentially regularization plus energy estimates. And this is the approach to build the resolutions. And we can essentially perform these two approaches also in the class of similar solutions. And what we get are the following statements. The first is about small data. So assume that the external body force is small in any norm is going to work, let's say small in L2. U0 equals 0, as I said. Then there exists a unique resolution and moreover, this follows essentially by uniqueness, U is self-similar with a smooth self-similar profile. Okay. So zero initial condition and small self-similar body force gives existence and uniqueness and also regularity. The only singularity is at the origin here because of the self-similar structure. When t goes to 0, this becomes, at t equals 0, this is a bit singular. But for t positive, this is a super great, beautiful solution to the Navier-Stokes equation. Now, what about general body forces? So, of course, we can build a resolution. So, given any f, u0 equals 0, we can build a resolution by means of the energy method. But given that uniqueness is not known, it's not clear whether the resolution you build is self-similar. It might be any solution in the energy class with a self-similar body force. It is actually possible to build a global self-similar solution in the Leray class, but a priori we don't know whether it is unique or not. A posteriori it is not, but let me write the statement. So this is general data. So pick f smooth with compact support, u0 equals 0. Then there exists uxt equal 1 over t 1/2 capital U of c, the resolution. And again, U is good. U is smooth. The smoothness is actually, once you have a similar solution, you can bootstrap the regularity of the profile up to C infinity. So the smoothness is not really the part. So here the key point is that even though I'm not assuming any smallness, I get a global self-similar solution. This is highly non-trivial actually. You can get a resolution, but getting exactly a self-similar solution is not trivial. The first result in this direction has been proven by Jien's work in 2004. And they considered the case of 0 external body force and -1 homogeneous initial condition with certain Holder type regularity away from the origin. And maybe the easiest way to prove this result is by applying a fixed point argument, but a topological fixed point argument. There's no contraction here, there's no smallness going on. You have to apply some topological fixed point argument. While here is the usual straightforward contraction principle. I mean, it's essentially the same proof as in the case of small data in L3 or whatever. And notice that the L2 norm, here I can pick essentially whatever norm, because any norm is critical in similar variables, because f is the similar profile is already critical. So anytime I mean, given any possible norm, if the similar profile is small, I can re-understand this in terms of a critical norm of small f. So this is nothing but the very same moral of well-posedness for small data in critical spaces. Really nothing new. This is something else. It's much harder result. Okay. Good. Now, we have some similar solutions. We know that for small body forces, they are unique. We know that they always exist, but maybe they are not unique when the body force is big. So it's kind of natural to try to study. I mean, we can pick any reasonable body force. We can add the parameter, put it in front. When the parameter is super small, we have well-posedness of the problem, and then we can try to increase the parameter and try to look for some bifurcation or something in order to get no uniqueness. So let's make this more or less rigorous. No uniqueness scenario. So let's consider this parameter kappa non-negative. And now my body force is F depending on kappa equal kappa over T power 3 half, capital F of C, and maybe we normalize capital F in order to have L2 norm equal 1. So when kappa is small, we have a unique solution. So in particular, we can build a curve of similar profiles. Kappa goes to capital U of kappa, where capital U of kappa is the only similar profile in the giving rise to the unique resolution associated to body force Fk when k is small enough. You have only one possible UK. And you can check that as soon as kappa is very, very small, so within this range, this gives rise to a very nice curve. This kind of regular. Now the question is, what happens when we increase k? Are we able to keep building this curve? And is it maybe possible that at some point this curve bifurcates or something crazy happens? And the key object to study is the linearized operator of the Navier-Stokes system. Either is here. Linearized operator. So imagine that we have been able to continue our curve up to a certain k equal kappa equal kappa bar, and we would like to understand whether we can keep continuing the curve or not. Now, if you study, I mean, at k equals kappa bar, at kappa equals kappa bar, we have this exact solution to the Navier-Stokes equation in the signal coordinates. Now, when you move a bit kappa, you are looking for small perturbations of this. Let's call V a small perturbation, so V is small. Now, if you plug U equal U kappa bar plus V into the Navier-Stokes equation in similar coordinates, and you check which equation is solved by V, you you get something of this form, d tau v minus ab. So remember, a is the diffusion part in this coordinates. Plus, I'll use the Leray projector to get rid of the pressure. So I get P divergence of U kappa bar tensor V plus V tensor U kappa bar. And then I get plus P divergence V tensor V equals 0. This is what you get. I'm using that U kappa bar solves the Navier-Stokes equation with body force F. Now, I'm assuming V very small, so the most important part of the equation is the linear part rather than the nonlinear part, so I'll simply drop the nonlinear part and study the linear part. And this operator here, as an operator of V, is the linearized operator of Navier-Stokes in some similar variables around U kappa bar. And let's call this minus L kappa bar of V. This is the key operator to understand. Okay? Now, a few remarks. If L kappa bar is invertible, you should think of it as an unbounded operator is actually closed and densely defined in L2 sigma, where L2 sigma is the space of L2 velocity fields with zero divergence. If it is invertible, or in other words, the zero vector field does not belong to the spectrum of L2 bar, then we can continue our curve. And this is not super immediate, but in the end it boils down to implicit function theorem. So I mean, it's pretty standard. So essentially you want to solve this equation, this equal to 0, you have this perturbation, you think of it as small since P is small, and if you can invert the whole linear operator, you can set up a fixed point argument, or you can simply write down a reasonable function and show that it is invertible by means of the implicit function theorem or inverse function theorem, whatever. You can do it in 100 different ways. It's kind of pretty standard once you know that this is invertible. Okay, but on the other hand, we can check, and maybe here we can do some formal check. Do I want to erase? Let me see. So on the other hand, we can check that if kappa is small enough, then the spectrum of L kappa is contained in the half space real part strictly smaller than 0. So actually, you can go even below, strictly smaller than -1 over 2. And here the spectral gap of the diffusion operator A is playing a role. So when kappa is very, very small, not only L kappa is invertible, it's very, very stable. And when I say that a linear operator is stable, I mean that all the eigenvalues have a real part strictly smaller than 0. And I'll say that an operator is unstable if you can find an eigenvalue with real part positive. And why is that? Well, yeah, for sure.
Because before you claimed 1/4 with respect to gap of A, and now you claim a half. Is that really what you want?
Yeah, I mean, I wanted to put any number slightly bigger than 1 over 4.
So you don't want to put them back.
I don't want to put
Maybe the minus, but you want it further to the right.
let me check, maybe.
I would have written 1 over 8, maybe, but we're going to miss it instead.
No, you're right, of course, thank you. Yeah, I mean, the sign minus in front, yeah, thank you very much. I mean, let's put positive and, I mean, yeah, you're right, thank you. Yeah, I mean, let me draw a picture. This is the complex plane. This is minus 1 over 4. We know that the spectrum of A is contained in this half space. What I'm saying is that L, and we can think of it as a kind of perturbation of A, somehow. When kappa is very small, is a small perturbation of A. So maybe the spectrum of L shifts a bit, but cannot go too far. And minus 1 over 8 is a good place. Okay, this is what I meant, thank you very much. But let's see, let's see at least formally why. I mean, this is already almost a proof, but let's make it slightly more rigorous. Pick any lambda over here with real part bigger than minus 1 over 8. I want to show that lambda minus L kappa is invertible then. Then this is invertible. At least if kappa is very, very small. Okay? Now, lambda minus Lk can be written as lambda minus the diffusion part plus the other term. Let's give it a name. Let's call the second part K of kappa. And here we have K of kappa. But now, the real part of lambda is bigger than minus 1 over 8, so it's definitely bigger than minus 1 over 4. This operator is invertible because of the spectral gap on capital A. So you can write this as identity plus K of kappa times lambda minus A to the minus 1 times lambda minus A. Okay? Now, it turns out that, this is invertible. So, that's plain rule. This operator over here is very, very beautiful. So, this is compact, to start with. And why is that? Well, the operator A, in the end, is nothing but a diffusion. So the inverse of the operator A is like a green function of the Laplacian. So it gains you two derivatives. The operator kappa is not so bad. It loses one derivative, divergence over here. But on the other hand, if your profile u kappa bar decays a bit at infinity, it gives, so in combination with the gain of two derivatives, it gives some compactness. So when you combine the two, you gain one derivative, plus the fact that this decays a bit at infinity gives compactness. Okay? So it is very nice. But actually, when kappa is small in the operator norm, as an operator from L to sigma to L to sigma, as kappa goes to 0. Why? Again, it is proportional to u of kappa bar, and u of kappa bar solves this equation with body force kappa times something of size 1. An easy energy estimate shows that u of kappa bar should be more or less of size kappa, cannot be too big. And so when kappa goes to 0, the body force disappears, the only solution is 0, and the operator becomes trivial, and therefore the operator norm goes to 0. You can make this rigorous, it's not hard, it's a bit of analytic work. So this is super beautiful, it's compact, so in particular this is a Fredholm operator. When kappa is small, this is very small in the operator norm. So this is nothing but the perturbation of the identity, and the small perturbation of identity is invertible. Invertible, invertible, invertible. Okay? As simple as that. So let's see. Yeah. L sigma is the L2 sigma. Is the space of L2 velocity fields. Zero divergence. Thank you. Okay. Now let's combine this observation and this implicit function theorem to build some reasonable picture. Now, if we denote by S kappa the biggest eigenvalue, the biggest real part among eigenvalues of L kappa, so we know that when kappa is small, this S kappa is smaller than -1/8. So we can draw a picture. So here we have our kappa, and here our S. So when kappa is very, very small, S is even negative. Something like this. Maybe another important observation. This S is actually, this is not a supremum, this is a maximum. And again, the motivation is more or less hidden here. So if you look at this decomposition and use the compactness of this operator, you realize that this is Fredholm and this is a super nice invertible operator. So this together with, some results in spectral theory tells you that in the half space -1/4 plus infinity, the spectrum of the operator Lk is discrete. There are only finitely many eigenvalues, and each of them has finite algebraic multiplicity. So in particular, you can pick the one with the biggest real part. It exists, and it's going to be finite. And this real part is denoted Sk. So we start with k very, very small. We have our curve of vector fields uk, and Sk is strictly smaller than something. So we can keep continuing our curve since the operator Lk is invertible. We keep extending, this gives rise to a super regular curve of Sersinger profiles. It might happen that at some point, at some k bar, the eigenvalue with the biggest real part crosses the imaginary axis. At some point, it might happen something like this. If it does, you get some eigenvalue with positive real part, or in other words, the operator Lk becomes unstable, and this is going to give no uniqueness. And let me write down a precise statement. Theorem. Instability implies non-linearness. So assume that at some point we got a velocity field, self-linear profile u bar. Let's assume some good regularity and decay, zero divergence, with associated force capital F. You should think of it as one of these UK once we cross the imaginary axis. And let us assume that since we crossed the imaginary axis, the linearized operator associated to u bar, which is the usual minus AU plus P divergence of u tensor u bar plus u bar tensor u, is unstable. And what I mean precisely is that there exists lambda in the spectrum of L with real part of lambda positive, and we can actually pick the most unstable eigenvalue, since we know that there's one with the biggest real part. So the real part of lambda, let's call it A, is positive, and this is the most unstable. And there exists an eigenfunction in L2 sigma, and actually you can check by regularity theory that if you get an eigenfunction, it has to be hk for every k, by parabolic regularization essentially, such that L eta is equal to lambda eta. That's the meaning of being unstable. So, under this assumption, you can build what I denote by U-lin, so the linear evolution of the unstable mode, which is nothing but the real part of e to the tau lambda eta xi. And you can easily check that this solves the equation d tau equal the linearized operator, essentially. I mean, if you have an eigenvalue e to the if you have an eigenvector e to the eigenvalue times time is a solution to the time-dependent evolution. So this solves d tau U-lin equal L U-lin. And moreover, since the eigenvalue is unstable, the real part is positive, this converges exponentially fast to 0 at minus infinity. And remember, minus infinity is our origin. So this is becoming smaller and smaller at minus infinity. Then there exists what I denote by U pair of xi tau. This is smooth. It decays at minus infinity even faster than U-lin. You can check that U tau in, for instance, H1 is smaller than e to the 2a tau for every tau small enough, smaller than a certain log capital T. So we have a certain time of existence, capital T, for this U pair, log capital T. And this has to be understood as a small perturbation of U-lin. And it decays at minus infinity with speed 2a, twice the speed of U-lin. And this 2 is related to the quadratic nonlinearity of the problem. And what's the point of this U pair? U pair is the perturbation that you have to add to U-lin in order to get a solution to the nonlinear Navier-Stokes equation, instead of a solution to the linear problem. So U obtained by adding the unstable object plus the linear evolution associated to the unstable mode plus the perturbation solves Navier-Stokes insert similar in minus infinity log t. This U, capital U, is the second solution. The first solution is U bar. U is the second solution. So if we go back, yeah.
Over there is the epsilon norm of P, which is...
Sorry, I meant U per.
And then the parameter for the exponential is tau and...
A. A is the real part of the unstable eigenvalue. It is twice 2 times 3. Now let's try to understand what is going on. So morally speaking, this is nothing but the construction. Yeah.
Maybe this is maybe better. I don't understand. So you need and also you do not depend on tau.
You lead does depend on tau. Tau is here.
Ah, that is tau. Sorry. Okay.
Yeah, I read it better. So U-lean is nothing but pick the unstable mode and evolve it with the semi-group associated to the linear operator.
Okay.
Being an eigenvalue, the semi-group just is e to the correct power times itself.
Okay.
Okay? Now let's try to figure out what is going on. Morally speaking, this is nothing but U is nothing but the nonlinear trajectory tangent to the linear unstable modes. Or if you want, is one trajectory in the unstable manifold associated with the unstable linear space at the critical point U bar, from the point of view of ordinary differential equations. From the point of view of the Navier-Stokes equations, let's go back in physical variables. In physical variables, we get standard variables. We get U bar of xt, which is essentially the similar solution associated to the unstable object. And that's a perfectly nice solution, belongs to the energy class, is smooth when it is positive, is a solution. We have our body force Fxt driving the dynamics, which is obtained by, again, writing in physical standard coordinates the body force capital F. But then we have built this Uxt, which is the sum of this U bar plus what I call the U-lean, which in physical variables is 1 over t lean x over square root of t log t, plus the last perturbation, U per 1 over t 1/2 c over square root of t, x over square root of t log t. Now, you can check that when t goes to 0, U bar converges to 0 in L2. This is because capital U bar is moved with compact support. So check the L2 norm depends on time, and it converges to 0 at a certain power law rate. Now, this object over here, we can call it the small U-lean of xt. This is smooth in space and time, and if you check the L2 norm, it converges to 0 at a certain L2 norm of U-lean xt. It converges to 0 as t goes to 0 with a certain power law rate depending on A, the unstable eigenvalue. The bigger is A, the faster is the convergence to 0. If you pick A big enough, this is converging to 0 way faster than this. And this is because instability tells you that in self-similar variables, capital U converges to minus infinity at an exponential rate, e to the a tau. When you change variables with a log, you get a polynomial convergence, which is power law depending on A. The last term, U per, which has to be understood as a perturbation, which is essentially what you have to add in order to solve the nonlinear equation rather than the linear equation. This U per again converges to 0 at the power law rate, but way faster than ulin. So this is telling you that ulin is way bigger than U per. So the sum of the two cannot be 0. This is a very small perturbation of ulin. So ulin is different from 0 by construction. U per is way smaller than ulin. The sum of these two gives something different from 0, converging to 0 as t goes to 0. So all in all, you got a second solution as a perturbation of the self-similar solution, as a smooth perturbation of the self-similar solution. Okay? And at the level of regularity, so if you want to check the regularity of the solutions, well, the regularity is the one of the self-similar solution. It has a self-similar structure with a smooth, compactly supported velocity to U bar. What we added here is simply smooth. Is it somehow clear? Okay, yeah.
So here we built this additional solution from one unstable eigenvalue, the most unstable one. Do you get such a solution for any?
You can, if you want, yeah. It's easier to deal with the most unstable because of technical reasons. So in the end, the proof of this theorem is a fixed point argument. And the key ingredient in the fixed point argument is a sharp growth estimate of the norm growth estimate of the semi-group associated with the operator L. And the growth is going to be dictated by A, the real part of the most unstable eigenvalue. So if you just construct the most unstable manifold, you can simply write Duhamel and apply contraction, it works. If you want to build all the other modes, you have to project into the correct eigenspaces, and then you can do that. Okay? Maybe I'll check the time because I'm not sure. 15 minutes. Oh, nice. Okay. Maybe I'll do it for 15 minutes. Yeah, so at this point, I don't want to elaborate more on the proof of the instability implies no uniqueness, because, I mean, in the end, it's nothing but building the unstable manifold in the linear list. It's more or less standard. It's just some fixed point, some very smart fixed point argument, nothing more than this. So I hope the whole picture makes sense. But now, to conclude no uniqueness, we need to build something unstable. So we can either, yeah.
Can you please also maybe write down what you explained, like to summarize, to write it down?
I mean, to summarize the whole thing.
Yeah, like when this bar is also a solution, like this.
Okay, yeah.
Just to write it down a bit because it just explained it.
Yeah. Well, U bar, so what we have is capital U bar given by that theorem over there. Given capital U bar, we generate F. We simply put capital U bar into the Navier-Stokes equation. It does not depend on time, so we only have this part. And this generates the force, capital F. The force capital F is smooth with compact support because U bar is. Given capital F, we can define small f. And small f is the body force in our original Navier-Stokes problem now. And again, given U bar, we get small U bar. And this is going to be the first solution, the purely self-similar solution of our Navier-Stokes problem. So the Navier-Stokes problem in physical variables is this, in standard variables. Now, given U bar, we generate capital F and we generate small f. And small f is the force giving no uniqueness. But given U bar, we also generate small U bar, the associated self-similar solution, and essentially by definition, this is going to solve, is a solution to an S. And you can check that is Leré. It's very easy. It's way better than Leré, but in particular is Leré. Now the point is how to build the second solution. The second solution has been built again by the theorem over there. The second solution is a perturbation of the first solution, and is given by adding ulin, actually small ulin, when you go back in physical coordinates, and u per, the perturbation that you need to make this solution to the linear problem. You can check that ulin and u per, the sum of ulin and u per is different from 0. They converges to 0 as t goes to 0. So this u gives a second solution to the Navier-Stokes equation, different from the first one, with 0 initial condition as well. And with the very same irregularity, because it's a smooth perturbation of the first solution. Okay? Yeah.
Usually I can ask yet how we solve the progressibility for U.
Because capital U bar is divergence free by assumption, so the first one is divergence free. The second fixed point, is part of the statement, so the fixed point argument is done in the space of divergence free vector fields. So ulin is automatically divergence free because eta is divergence free essentially by assumption, so ulin is divergence free because eta is divergence free, and u per is obtained by perturbation into the space of divergence free vector field. So the fixed point gives you something which is already divergence free. Yeah?
So since U bar is smooth, then there's also no weak strong uniqueness.
U bar is smooth, capital U bar is smooth. Small U bar is not. That's the capital U bar is not at t equals 0. It's smooth when t is positive, but is not at t equals 0. That's why the solution is not classical. It's singular at least at one time. But yes, you have weak strong uniqueness when t is positive. The point is how you reach the origin where the singularity is. Okay? Well, I wanted to say something about how to build instability, which is really the key point. I have like 10 minutes right. So instability. How do we build this U bar? So the key missing ingredient is the construction of U bar, and this is what we did in our paper. So essentially we built U bar smooth with compact support, zero divergence, such that the associated L operator is unstable. And this is essentially the hardest part of the work. And the idea here, very roughly, is to start from something which is two-dimensional and unstable for the two-dimensional evolution, and try to lift it in the three-dimensional framework. So the starting point is unstable vortex in dimension 2, built by Dishik. And the key idea is to try to kind of find a three-dimensional object having this unstable vortex as a section. And the natural, the one that worked out is a vortex ring structure. Vortex ring with unstable 2D section. So in the end, what we build, U bar, is an incompressible smooth velocity field, which is axisymmetric in a swirl. And it is really concentrated on a solid torus of dimension, the correct dimension in F3. And if you look at the section, so if you cut the section of this torus, what you see is a two-dimensional velocity field. And this two-dimensional velocity field is a perturbation of an unstable velocity field in dimension 2. And the whole point is to apply perturbation arguments to try to show that this two-dimensional stability survives when you place it in this unstable vortex. And regarding two-dimensional stability, there's essentially a general, more or less general construction to build unstable shear flows and unstable vortices, and it is based on reducing to an ordinary exponential equations the fact that vortices, maybe let me write on something otherwise. So, 2D instability. So I cannot explain in detail how to go from 2D to 3D, but let me maybe say something about what we can do in 2 dimensions. In 2 dimensions, there are many interesting steady states for the Euler equations with a lot of symmetries. Interesting objects to perturb are shear flows, vector fields of this form. And you can check the vorticity is going to be minus F1 LST. Those are essentially one-dimensional flows. And the ones very useful for this no uniqueness business are vortices. That are essentially shear flows but in polar coordinates. So they have the form u bar some radial profile times the angular vector field, and if you compute the curl, you get a purely radial function. And here I'm just using standard polar coordinates. So morally speaking, those are nothing but shear flows in polar coordinates. Now, the idea is that those are steady states. You can check that. U bar dot grad omega bar is equal to 0. This is essentially the Euler equation in 2 dimensions. The steady state Euler equations in 2 dimensions. And so you can look at the linearized operator, and the linearized operator is very easy to write down. The linearized operator in vorticity in dimension 2 is nothing but transport u bar dot grad omega plus the Biot-Savart law, the 2-dimensional Biot-Savart law applied to omega. If you remember, there's an explicit formula like grad per Laplacian to the -1 of omega, but it's an operator of order -1, grad omega bar. That's the linearized operator. It has a very nice structure in vorticity form. Indeed, the first term is a transport, and the second term is compact. If you have some decay at infinity of omega bar, this is going to be compact, because the Biot-Savart operator is going to regularize, it gives one derivative, it gains one derivative. And if this object decays at infinity, you are kind of cutting off your function, and this overall is a compact operator. So in particular, the spectrum is pretty nice. The spectrum is something like this. You might have a very complicated spectrum in the imaginary axis, but outside you only have finitely many eigenvalues with finite algebraic and geometric multiplicity. So in dimension 2 the picture is nice. I'll write down just the last equation and conclude. Finding a stable eigenvalue means solving a partial differential equation, this one, for a certain lambda with positive real part. Positive or negative, because in this Euler framework you can change the direction, and you can change the sign. And anyway, non-zero, the point is non-zero real part. There are essentially no general methodologies to solve an equation like this in the framework of the Euler-Navier-Stokes equation. What you can do in the specific frameworks of shear flow and vortices is to use the symmetries, so they are essentially one-dimensional objects. So you want to rewrite this problem as an ordinary differential equation. It is possible, and what you get is the so-called Rayleigh equation. Let me write it down and conclude. So for instance, in the case of shear flows, of shear flows, you have u bar given by fx2, 0. You can even assume for simplicity that the first variable is periodic and the second variable is in R. And then you realize that this operator is invariant. I mean, you have a very nice family of invariant subspaces for this operator. So if you write down the Fourier series with respect to the x1 variable, you realize that for every fixed frequency k, this gives rise to a certain subspace, and L is invariant. And it is also useful to consider the so-called stream function psi, and write the equation in terms of psi instead of the vorticity omega. And once you write the vorticity in Fourier with respect to the first variable, the one in x1, you get summation over k, ck of x2, e to the I k x1. So each of these are invariant under L. So you can restrict, you fix k, and you just look at functions of this form. And this is going to give you an ODE with respect to the variable x2. And the ODE you get in the end is the Rayleigh equation. Is second derivative is a Schrodinger type equation. Second derivative minus k squared applied to pk minus f second over f plus lambda over ik equals 0. That's the equation you have to solve. If you can solve it, so here lambda is given, is your eigenvalue, I mean, is the one you wanna, is the eigenvalue with positive real part. K is the invariant subspace you choose. F is given, is your shear flow. You want to find psi, solving this equation. If you have such a psi, you can use it to build the unstable model. And notice that in order to write the equation in this form, I'm already using that the real part of lambda is different from 0. Once the real part is different from 0, this number is never 0 because that is real. This is a Schrodinger type equation. It's actually very, very hard to solve. The key idea is to perturb what are called, this dates back to Tolmien, a physicist who gave this very interesting heuristic on how to solve the equation. And the point is a perturbation argument. So perturb what are called neutral modes. Particular points in the particular choice of parameters. And another easy observation from this equation, you can easily check by means of energy estimate that if f second, the second derivative of f, doesn't change sign, then you cannot solve this equation. You can never solve this equation. So integrate by parts against psi, and you will realize that you need some cancellation in f second. And this fact, f second strictly positive or strictly negative, but then the shear flow or the vortex is stable, is called the Rayleigh stability principle. So this is telling you that something non-standard has to happen. You cannot pick something convex or convex as a shear flow. So just to conclude, in general, it's very, very hard to study the spectrum of these operators, because those operators are not similar, there are no general techniques. The known results are based on very specific analysis on symmetric objects and reduction to ODEs, and even ODEs are very, very hard to treat. One, to me, very interesting open question is whether one can find a real PD, multidimensional PD technique to build unstable solutions to unstable steady states to the Navier-Stokes equations, or even Euler. And okay, I think I'll stop here. Thank you.
Thank you very much for the great lecture. Anyone dares asking a question?
I think yes.
You're loud enough for
Thank you. Well, I was wondering if you change this U lead function with different lambda, do you get different solutions? So, like, the step that I was thinking after this is that you have two different solutions, but one can ask, well, how large is the whole dimension of all the solutions? Is it like infinite?
I'm not sure I got your question. So here I stated it with two solutions, but actually you can build infinitely many simply by, I erased the theorem, but the construction depends on the eigenfunction eta of the operator L. But eta is not normalized, so you can pick constants times eta and run the construction. This is going to give an entire continuous family of solutions. But don't know if this answers your question.
Yeah, so you have infinitely many solutions, at least
You have
like
infinitely
one
many.
parameter.
You have at least one parameter, but you, in principle, you can build a huge space of solutions depending on the dimension of all the unstable modes. So you have many solutions here depending on